Well, calculus, we're on Unit 2, and you survived the Unit 1 on limits, so it's only going to get better, I promise you that. We're going to do a unit on derivatives. I think it would be very helpful if you were to compare the 4 definitions of derivatives, pages 14, 25, 65, and 68. They're similar, but slightly different, but you'll notice how the look is the same. Page 14 is the slope of the tangent, which is what we've talked about. Page 25 is velocity. Page 65 is the derivative, which is a new word to us. And page 68 is the derivative in the general case of f at x at a certain place x. So if you could make a definition or compare them in your notebook, I think it would be very helpful. Let's do a couple of examples together. The first one we're going to look at is find the instantaneous rate of change of f at x equals x squared at x equals minus 3. So we know we have a basic quadratic function. So we can get a sense of, there we go. We have a sense of what the instantaneous rate of change would be at minus 3. Okay, so that didn't go very well. Okay, so we would have a slope of a tangent at x is minus 3 approximately right there. So we have a picture in our head. Let's look at the definition for the derivative. The derivative, which is the slope of the tangent, is written like that. F prime of x, or the derivative of the function with respect to x, is the limit. So, okay, so we're doing limits for another couple days, but it's going to get better. The limit as h approaches 0 for the function at negative 3 plus h. So their difference quotient, and that will give us the instantaneous rate of change, aka the derivative, aka the slope of the tangent. F prime at negative 3 would be proper notation. Limit as h approaches 0 for negative 3 plus h squared, subtract, and the function's value at negative 3 is 9. At this moment, I have my 0 over 0 indeterminate problem, so I'm going to use expanding to tidy that up and get rid of the 0 over 0 problem. The limit as h approaches 0 for the derivative at minus 3 is 9 minus 6h plus h squared, subtract 9 over h. Coincidence? I think not, that the 9's cancel each other out. I have a factor, a common factor of h minus 6 plus h all over h. Super cool. If I divide out h from top to bottom, I am left with the limit as h approaches 0, negative 6 plus h would be negative 6. So it appears that the slope of the tangent when x is minus 3 is a slope of negative 6. That seems reasonable by our diagram. We also want to look at the general case. So I have the slope of the tangent at the place x equals negative 3, but can I just determine a relationship for the derivative? Let's look. F prime of x, or the slope of the tangent for this function at any place x, is the limit as h approaches 0 for this function at any x for the difference quotient. That would be the general case. For this one, I would have x plus h squared subtract, h squared, x squared. So I did it wrong here. There, all over h. If I were to expand, same process as I did with the negative 3, I would have x squared plus 2xh plus h squared, subtract x squared. What do you know? The x squareds cancel. This is so great. Factoring out a common factor of h, as I did in the specific case, I have 2x plus h over h. Divide out h top and bottom to get rid of our 0 over 0 problem. And then I can do a direct substitution of 0 and end up with 2x. So the derivative, when the function is x squared, the slope of my tangent, or my derivative, is 2x. Super cool. Our second example, we are asked to find the derivative, or the slope of the tangent, or the limit as h approaches 0 for the difference quotient, but I'm looking for it not at a specific place, but a general case. So if my function is root of t, then my derivative in the general case will be the limit as h approaches 0 for that function and I'm going to use the specific function square root function. All right, square root of t plus h, subtract square root of t all over h. If I were to substitute h as 0 right now, I'd have my 0 over 0 problem. So I need to use my algebra skills to tidy that up a little bit. The limit as h approaches 0. I want to rationalize the numerator for this thing to get rid of my 0 over 0 problem. So I'm going to multiply by the conjugate. Root of t plus h, subtract root t over h multiplied by root of t plus h, subtract root t over root of t plus h, subtract root t. I'm multiplying by 1, but I will be able to get rid of my problem. I'm going to put brackets in to remind myself my thinking is like FOIL. I guess I should put that on the bottom too and be consistent. I end up with t plus h. Outside, inside cancel. Oh, I didn't write that correctly. I hope you caught that. Opposite sign. Pause. Okay. Outside, inside cancel. Negative t all over h times ugly t plus h plus root t there. Okay, on the top, my two t's cancel. No more t's. I am left with an h on the top and an h on the bottom. I can divide out h's, and I am left with 1 over. I can put a 0 in there right now. I would have root t plus root t, which is 2 root t. This derivative would only make sense for t greater than 0. Otherwise, we've got a problem. And we also have our function was only defined for t greater than or equal to 0. But our derivative, we can't have a 0 on the bottom. Just a sidebar. Okay, last example. Find the equation of the tangent. So this time we want an equation. We want specifically at x equals 2. But I think for myself, I would like to find the derivative general case. And then I want to find it specifically a little later on. So what this is going to tell me is the slope of the tangent comes from the derivative. So let's do that and we'll figure out the equation in a moment. So my derivative is the limit as h approaches 0 for the difference quotient, which is f at x plus h minus, and you wouldn't have to write this one out every time, but not bad form. Limit as h approaches 0. That I need to write every time because I haven't taken the limit yet. So we keep writing it until we are done. So 1 over x plus h, subtract 1 over x, all over h. It's messy. If I put a 0 in right now, I get 0 over 0, so I need to use my algebra skills this time. I need a common denominator, and I'm going to deal with that over h just a little later. My common denominator would be x times x plus h. My numerator gets adjusted by a factor of x. My second numerator gets adjusted by a factor of x plus h. I can tidy that up now. My x's cancel. I am left with negative h over x times x plus h times 1 over h. I probably didn't need this line either, but I don't want to skip too many. So I have an h in the numerator and an h in the denominator. I can divide out a factor of x from top and bottom. And now I've gotten rid of my 0 over 0 problem. I can put a 0 in for h, and my derivative would be negative 1 over x squared. So my derivative is negative 1 over x squared, which tells me what the slope of the tangent would be for any x. If I want the slope of this particular place, I want the derivative at x equals 2. So using the general case, I have negative 1 over 2 squared is negative 1/4. So the slope of my tangent is negative 1/4 when x equals 2. Slope of tangent when I have been asked to find the equation of the tangent, which is why we did that silly review on the first day. So if I want the equation of the tangent at x equals 2, I have my slope, and I want to substitute any point that I know, and I want it specifically at that place. So I'm going to substitute this point into y equals negative 1/4 x plus b. Going back to the original function, when x equals 2, okay, just as an aside, when x equals 2, f at 2 equals 1/2. Doesn't show to hurt that thinking either. I'm going to substitute that point. I have 1/2 equals negative 1/4 times 2 plus b. 1/2 equals negative 1/2 plus b. Add 1/2 to both sides. I have b equals 1. Isn't that lovely? Final answer, y equals negative 1/4 x plus 1. So I kind of lied about the limits being done for good, but we are thinking a little bit different vocabulary. Words like derivative, derivative in the general case, slope of the tangent at a specific point, and we are still using our limit skills to be able to get there.